My name is Xiaocheng. I'm a postdoctoral researcher at McGill University. First of all, on behalf of all the organizers of the Mathelites Society, I'd like to welcome you all to the TMS talk. Today we have the honor to have Keena Trowell as our speaker, and she's going to tell us about her research on hydrogen production. And before introducing our speaker today, I will just introduce a bit about our society. And also today's event is organized by the personnel shown on this page. Today's event will consist of 4 parts, and in the first part I will give a introduction of our society, and the next my co-host Dr. Weiqi Ji, he's a postdoctoral researcher from MIT, and he's going to introduce our speaker today, Keena Trowell. And the Keena's talk will last for about 40 to 45 minutes. And after that, we will have the Q&A session for about 30 minutes. The Mathelites Society is a non-profit organization that aims to build a community for young scholars to freely and equally exchange thought and build interdisciplinary connections for research. And there are 4 major events that we organize. The first one is the TMS talk. For these talks, we invite researchers from academia to share us about their cutting edge and interesting research. And the second one is the WBA talk, which stands for World Beyond Academia, for which we invite professionals about different career paths that scholars or PhD students can. In this one, we will talk about some skill set or using tools for PhD students to get benefit for their research or the work after their graduation. And the last one is the special issue, which we will have at the beginning of each season. And this we will organize this based on the suggestion from our community. And for you, if you want to know more about our society, you can visit our website, which is linked here, or contact us by email. And also we list all the QR codes here for you to follow us on Twitter and WeChat. So next I will pass on to my co-host Weiqi Ji for him to introduce our honored speaker, Keena Trowell. Yeah, please go ahead, Weiqi.
Yeah. Hi, everyone. So I'm Weiqi. I'm a postdoc at MIT. I'm also working on combustion. So today it's my great honor to introduce Ms. Keena Trowell. So Keena is currently a PhD candidate in the Alternative Fields Lab at McGill University. So her research is focusing on using supercritical water oxidation of metals for hydrogen production and the use of metals as energy carrier. So she's also interested in energy storages and also the tech economic aspects of carbon neutral fuels. So can we go to the next one? Yeah, so before the talk, I'd like to mention some rules. So first, please mute yourself during the talk. And after the talk, you can ask questions either by using the raise hand function or write your questions in the Q&A chat. And also for each turn or each person, so you may ask no more than 2 questions. So yeah, so without more details, so let's pass to Keena's talk.
Great, thank you for the very nice introduction. So I'm just going to start by sharing my my screen here. So.
Sure.
Great, can everybody see that? Okay.
Yes, yes.
Wonderful. So I want to start today by talking a little bit about my motivation for doing the research today, or the kind of research that I do. And it really comes down to this, is that I've come to recognize that a transition to an energy system that's based on renewable and carbon-free sources of energy is inevitable. But we're not there yet. So the first question I get when I say this to people is that, well, you know, do we have enough renewables? So right now we use about, we have a global power demand of about 17 terawatt. Now, if we were to transition to renewables, that would drop to about 12 terawatt just because of the gains of inefficiencies that come from using electricity rather than other energy processes. Now, while we're sort of thinking about the energy system of the future, I also like to think about a world where everybody has access to all the energy they need. And so, you know, if this were the case, we would actually need about 40 terawatt to have everybody have enough energy in order to have a decent standard of living. Okay, so that's what we would need. And what do we have? Well, we have about 2 terawatt of hydropower available to us, another 40 to 80 terawatt of wind, and 580 terawatt of solar. And I want you to keep in mind that these numbers are based on technology that was considered feasible and scalable 12 years ago. So clearly the question isn't one of supply because we've got lots of renewable energy. But this renewable energy, well, really with the exception of hydropower, is it's variable and it's intermittent. And so the real challenge is one of storage and transportation. So how do we store that energy so that it's available whenever we need it? And then how do we move that energy around so that places that don't necessarily have a lot of renewable resources can still meet their power needs in a clean way? So what we need to fill this gap, to make these things, that supply and demand meet, is energy carriers. And the optimal energy carrier in such a system would be something that would be energy dense. It would have to be safe and easy to both store and transport. And then of course we would want something that's sustainable. Okay, so what are the options? Well, this is the periodic table. I'm sure everybody's familiar with it. And this is every known element. So really, we have to base our new energy carrier on something from this table. Now, because the way we get energy out of anything is through a reaction, we want something that readily reacts with either air or water. And so none of these are useful in that way. Because we want to be able to move this energy around, we want something with a high specific energy density. So anything with too high of a molecular mass is simply going to be too heavy to move around easily. We also want to avoid relying on something that's rare because that also just translates to expensive. And we, of course, would not want anything that's either toxic or that becomes toxic once it's oxidized. And at this point, I also like to take off potassium because we need that for fertilizer, and we want to avoid a situation where our energy system is competing with our food system. So I take that off now. So this is what we have left. And I don't think it's surprising that we see carbon is still there, and that's what forms the basis of our energy system now. But we can't keep using carbon, so I'll just take it off now. And we also see hydrogen up there, and hydrogen's getting a lot of attention these days, and has actually for the last couple of decades. Hydrogen, we can make it just using water and renewable electricity. And when you burn hydrogen, like in something like a gas turbine engine, the only product left over is water. That's the oxide of hydrogen. Or you can use it in a fuel cell, and again, the product is water. So it has this carbon-free energy cycle. So why hasn't the hydrogen economy been rolled out? Well, it comes to this idea of energy density. And I've said it before, so here I'll talk a little bit more detail. So the reason hydrocarbons are so convenient is because they have a high energy density, which just means that they contain a lot of energy in a small, relatively light package. So if you think about the amount of energy that would be held in some container of diesel, it doesn't matter what size the container is, just some container. If you wanted to hold that same amount of energy, but rather than in diesel, in say liquefied hydrogen, you would need 5 containers of the same size. And so if you start to think about, okay, what would that do to say a car, or storing that or transporting that, you can start to see how a hydrogen, even in liquefied form, which is the densest form of storing hydrogen, why it's so challenging. Now, there's also what you can do with hydrogen is you can stabilize the hydrogen with a nitrogen molecule and make ammonia. And with ammonia, you could carry around that same amount of energy. You would just need 3 cases. So it's a little bit better. But of course, ammonia is also toxic. So so that doesn't fit our criteria that we laid out earlier of having a non-toxic energy carrier. So hydrogen, what I always say about hydrogen is that it's a great fuel, but it's a lousy energy carrier. And so once we take that off, what we have is this handful of metals. And in a way, we're already using metals as energy carriers. So if you take, for example, lithium here, lithium, if we wanted to, again, just comparing it to diesel, if we wanted to carry the same amount of energy, we'd only need about 1.5 cases, which is great. But we don't use lithium directly. Instead, what we do is we take that lithium and we make a lithium ion battery. And batteries, because they have to carry around their fuel and their oxidizer, they have, I think there's one more. They have a very low energy density and also specific energy. So in terms of their mass and volume, they carry relatively little energy. Now, that's not to say that batteries are useless. No, batteries are great. Batteries are great for a lot of applications. They're great for phones. They're great for laptops. They're great for everything up to about a passenger vehicle. Lithium ion batteries do really well. But when we're talking about large scale seasonal energy storage or an energy trade, their energy densities are just too low to allow that. But what if we can use that, the energy in metals directly, right? So we get away from having to build a battery, we just use that energy directly. And here I'm going to show 2 that I think are quite promising, which is aluminum and iron. And you can see here that, again, compared to diesel, if we wanted to carry around that same amount of energy, we'd only need about half a container of aluminum or about the same size container of iron. And so these metals, in short, are energy dense. They're safe to transport. We do it all the time already. They're safe to store, and they're recyclable. Now, I picked aluminum and iron for a reason, and that's because we need to look at not only, it fits these criteria that I laid out, but how much do we have left, right? So let's just do a little thought experiment here. So let's say for whatever reason, we decided we wanted to take the global energy demand and put it into just one fuel, just one energy carrier. If we did that, this is how much we would need of each one. And so here I'm showing it in terms of mass. So here this is just a reflection of the specific energy of each of these metals. And so this is how much we would need. And now we can take that and compare it to the known reserves of each metal. And so you can see here that iron, aluminum, and silicon are the only ones where what's available to us, the reserves, actually outpace what we would need if we were to do this thing. But because the metals are recyclable, it's not as if we would run out of, say, iron in 3 years. No, we would just have that initial amount of iron, and then we would recycle it over and over and over. So it would be a closed loop. Now, speaking of closed loops, this is how we in the Alternative Fuels Lab envision this metal fuel cycle. So the first bit here, actually, you know what? This is a good time for me to get out the laser pointer. So this bit here, this is where your smelter would be located, or your iron reduction facility. And so this is where you would locate this where you have a lot of renewable electricity available to you. Now at this point, I'm often interrupted, and I haven't been now, but somebody will inevitably ask, okay, but isn't this expensive? Metals are expensive, isn't this expensive? So I want to show you another quick plot before I go back to that cycle. This is the electricity prices over the last 12 years or so. And you can see here that electricity derived from coal and combined gas cycle have been relatively steady over this time period. And this is just at utility scale. Now, if you look at what's happened with solar, you can see that it has dramatically reduced over the same time period. And starting in about 2015, utility scale solar, unsubsidized in the US, actually has become one of the cheapest ways to produce electricity. So before, we had this paradigm where you had cheap fuels, and so you would use your cheap fuel to make electricity. But now we have the opposite situation where we have cheap electricity. So now it's starting to make more sense to take that cheap electricity and produce fuels. And then that way it's allowing us to use that primary electricity in more applications. So back to the metal fuel cycle. So here so this is where you have your cheap renewable electricity, wherever it's available in abundance, that's where you would locate your smelter. And then you would reduce the oxide into the metal here. And then that metal is now effectively storing that clean energy. And because it's metal, it can do that for a long period of time without degrading or prematurely oxidizing. And because it's now in this energy dense and material with a high specific energy, now it's in a form that can easily be transported to wherever it is it's needed, or even stored locally for use. So, if you're like in Canada where you have a lot of solar in the summer, but not so much in the winter, you can just keep that metal on site and use it later in that same year. When the stored energy is needed, it's oxidized, and that releases that energy, and that can be fed into a variety of engines and other prime movers. And the nice thing about this is that it's also quite scalable. So you can have small scale, sort of at the kilowatt, all the way up to gigawatt power. And the other product, besides this clean energy coming out, is the metal oxide that's left over. And because they're solids, it's easier to collect them, and they can be collected and then transported back to that smelter where you have that abundance of renewable energy. And so that's how we envision this metal fuel cycle working. Now, there's two ways to oxidize metals. One is what we call metal air reactions, or direct combustion, which is burning the metal in air. And because there's no carbon present, we don't have to worry about the emission of carbon dioxide or monoxide. And the other way of oxidizing the metal, which is what I do in my research, is through using water as the oxidizer. And so here, rather than heat being the product, which is the product of combustion, you have the production of heat and hydrogen. And again, this heat and hydrogen can be fed to a variety of engines for your power needs. Now, in my research, in terms of my PhD, I really focus here on the reaction itself. So for the rest of the talk, I'm really just going to focus on metal water reactions and some of the work that I've done in the lab. So this is the global metal water reaction, but specifically when we talk about aluminum, it can follow one of three pathways, and the pathway that it follows depends on the temperature and the pressure conditions inside the reactor. But what I want to draw your attention to is that given the same amount of aluminum in each case, you have the same amount of hydrogen produced and roughly the same amount of heat. The only thing that changes is the stoichiometric amount of water here. And then that extra water will show up in the products here. So this reaction is the one that produces the oxide, or the completely dehydrated oxide. But in the regime that I work in, we end up in this region here. Now, aluminum is a highly electronegative material. And because of that, it has the formation of like a passivation layer right on the surface after any exposure to oxygen. And so that's why you can have aluminum siding and aluminum in your car, and it doesn't produce hydrogen as soon as it gets wet. It's because of this passivation layer. And this passivation layer, it's about 2 to 3 nanometers thick, and it's there as soon as any exposure to air, and it's always about that thickness, despite the bulk aluminum beneath, and it does a really good job of protecting it from further oxidation. But because of this passivation layer, the reaction interface in a metal water reaction isn't at the surface of the particle, but rather it's here where the passivating oxide meets the bulk aluminum beneath. And as a result, there's 3 phases. The reaction proceeds in 3 steps. The first step is what we call the induction phase. And this is where that passivation layer is hydrated and weakened through the motion, or through the OH ions will migrate through that and effectively weaken it. Once it's sufficiently weakened, we have what we call the rapid oxidation. And during rapid oxidation, this is where you have that evolution of both the heat and the hydrogen. And at the same time, on the surface of the particle is a formation of this oxide or hydroxide layer on the surface of the particle. Now, as the reaction proceeds, this layer gets thicker and thicker and denser. And eventually one of two things will happen. Either all of the metal in the system is consumed and the reaction quenches, or the oxides on the surface of the particle become so thick and so dense that water can no longer migrate through, and the reaction will quench that way. And in the second case, you have this little bit of unreacted fuel right at the center, and so this is effectively just wasted fuel. Now, a lot of the research in this area has really focused on shortening this induction period here, and that way you can get this rapid oxidation and get much faster reaction rates. So here I've just listed sort of the four most common approaches, and they're all effective. And if there's questions afterwards, I can go through sort of the mechanism of how each of them works. But I just wanted to draw your attention to this one, is the use of alkaline catalysts. So if you have something like sodium hydroxide, calcium hydroxide, or potassium hydroxide, that will increase the pH of your solution, which means that your solution has more OH ions in it. And the fluid that has more OH ions in it means that there's more OH ions that can sort of attack that passivation layer and have that reaction happen more quickly. And this presence of OH ions I'll come back to that later, but it's very interesting for this research. Now, all of these approaches are effective. They do increase the reaction rate, but they have drawbacks, and I've listed them here. But the main drawback that they all have, which to me is sort of the worst one, and the one we can't get around, is the low reaction temperature. So this low reaction onset temperature is a problem for two reasons. One is that if you have aluminum that can react with room temperature water, you can imagine that there's a lot of opportunity for accidental exposure, or accidental oxidation after, if you have your powder there and it gets wet, and then you have the formation of hydrogen in your space. That's extremely dangerous. And the second challenge with it is that in an aluminum water reaction, about half of the energy will evolve as hydrogen and the other half as heat. And so if you have a low reaction temperature, then the heat that's produced is a low quality heat, which means it's not mechanically useful. And so you can't use that to turn a turbine or anything like that. And so you're effectively just wasting half of the energy. So that low reaction temperature, it's both dangerous and wasteful. So in my research, I went in the complete opposite way. I looked at increasing the reaction temperature. And so if you're familiar with this expression, it's the Arrhenius expression. And basically what it tells us is that the reaction rate will increase exponentially with the increase of temperature. And earlier work in our group showed that. So just very modest increases. So this is the same powder. You can get almost a doubling in the reaction rate with a relatively modest increase in temperature. In this case, just 35 degrees Celsius. And then if you were to integrate this curve, so take that area underneath the curve, well, that corresponds to the yield of your reaction. So you can see here that going up in temperature increases reaction rate, increases reaction efficiency, because you can get higher yields. And so that's really where my work started. And I wanted to see what we could do about this bit of unreacted fuel. So the thinking in the field before was that, with a given temperature, or with a given sized powder and a given temperature, there was this sort of upper limit to how much or how complete the reaction could be, how efficient that reaction could be. And these curves are just extrapolated from all of that low temperature data that was out there before. So you can see here that basically what this thinking implies is that those oxides and hydroxides that form will prevent complete oxidation. And so a 12 micron powder, you could reasonably expect to get full oxidation or complete hydrogen production with liquid water at about 350 degrees or so. But if you went up to 120 micron powder, so, you know, a 12 micron powder, think something that has the texture of maybe bread flour, 120 micron powder, something that has maybe the texture of beach sand. Well, with that, you can only reasonably expect about 30% yield just by going up in temperature. But I mean, I guess I wasn't convinced because I'd read about what happens with water as you go up in temperature, and I thought that there might be something else there. So we designed this experiment. And so in each experiment, I would use this high temperature, high pressure reactor that could hold the pressures that would be involved in the experiments I wanted to do. And for each experiment, I would load in a measured amount of the powder that was, or the aluminum that I was working with, and a measured amount of water as well. Now the water was calibrated so that the metal would always be in contact with liquid water, and that once we reached the critical point, so once the temperature was at 373 degrees, that the density of the water would also be the critical density of water. So once that was all loaded in, the reactor is sealed and heated up to the temperature of interest. And then I would hold it at that temperature for a predetermined amount of time before cooling it back down to room temperature. And to determine the yield, I would take the final pressure and the initial pressure, and the difference between those, just using the ideal gas law, we can calculate how much hydrogen gets produced. So this is what the actual lab setup looks like. So there is the reactor there, covered in insulation. It kind of looks like a little burrito. It only has an internal volume of about 120 mils, so it's quite small. And there is a thermocouple, so we can take pressure measure or temperature, and then there's a pressure transducer, so we can take pressure, and all of this data is recorded on a data acquisition system that's not pictured. And below here, I'm showing what a typical pressure trace would look like. So the blue line is what was measured. The black line is the vapor pressure at that temperature, because we're taking temperature measurements, so we can calculate that at every point. This initial increase is just due to the heating of the water. And then we see a point where there's a divergence between what we would measure and what we would expect from just the vapor pressure alone. And so that tells us when the evolution of hydrogen begins. And the difference between these two lines is that pressure that is due to the evolution of hydrogen within the system. But I'm gonna just mention here that with this experiment, how it was designed, we can't reliably determine rates because there's a certain amount of dissolution of hydrogen into the water. And I can talk more about that later if people are interested, but that's why I'm not reporting any rate data in this talk. So as I mentioned a second ago, this is what would have been expected just based on the low temperature work that had been done in the field and extrapolating to higher temperatures. But instead, this is what I found. These were the results of my experiments. So you can see here that up until about 250 degrees Celsius, there's pretty good agreement between the prediction and the measured. And then there's this transition between about 250 degrees and 373 degrees, or the critical point, where there's a marked increase in efficiency that wasn't predicted. So with the 12 micron powder, it's very subtle, but you can see here with a 20 micron or 120 micron powder, it's almost a vertical jump, and we start to get full production. So naturally, I wanted to see, okay, like how big can we go? Like, can we go to much larger particles? And so I used aluminum slugs that measure about 3 millimeters in length and diameter. I also used aluminum plates, which were about 2 millimeters thick, and then a common aluminum can. And with the aluminum can, I did 2 sets of experiments. In one set, it was just the can was cut up so that it could be loaded into the reactor. And in the other set of experiments, I had a summer student. She was very kind to spend all this time sanding off all of the linings and the brand markings and everything. So we would just be left with the aluminum alloy material. And so we can see here that again, up until about 250 degrees, there's no change. There's no significant hydrogen production. And then again, this transition zone. And then once we get into the supercritical zone, there's full reaction or full oxidation in every case. And so looking at figures like this is one thing, but I wanted to show you what the actual products look like. So these are the aluminum slugs. They're nice, they're shiny, and you know, they come in a little bottle. And then this is what they look like after sitting in water at 250 degrees for 30 minutes. And you can see here that there's very superficial surface roughening, but from the pressure trace, we can see that there was no significant hydrogen production. And then at 350 degrees, so in that transition zone, you can see here that the oxides or the slugs start to sort of crumble and disintegrate, and they're not really, like they're losing their shape. And then in the supercritical water, you end up with this extremely fine powder. So the goes from a reactant, that's that 3 millimeter scale, to a powder that's on the order of about 30 micron. And it's even more remarkable when we look at what happened with the aluminum can. So this is the aluminum can with all the coatings and brand markings still on it. And so you can see here that, you know, at 300 and 350 degrees, there's very little change. It's very superficial, and from the pressure trace, no hydrogen production. And then at 380 degrees, so just 30 degrees higher, again, this extremely fine powder, again, on the order of about 30 micron. And, you know, I thought this was very remarkable, and we'll talk about that in a second. But first, I want to talk about this transition here. So, you know, in the traces, we can see it here. And this can be explained because of the changes to the water itself as water goes up in temperature and pressure. So at 250 degrees, the ionic product of water is at its peak. And so what the ionic product is, it's the product of the concentration of H ions and OH ions. And so if you remember before, one way to catalyze a aluminum water reaction is to use is to add something basic to it, so something like potassium hydroxide. But here we get the furnishing of these OH ions. We get a higher concentration of OH ions just because of what happens with water as you go up in temperature and pressure. And so just by going up in temperature and keeping the reactor sealed, we're in effect self-catalyzing this reactor or this reaction, and we're creating a situation where there's enough OH ions to attack the any remaining passivation coating, and so that way the fresh aluminum beneath is actually exposed to the oxidizer. And then here in the supercritical regime, so with the 12 micron powder, we did get full oxidation at lower temperatures, which was, you know, wasn't so surprising. But you can see here that in the larger samples, the thicker samples that were predicted to only have, you know, 30% yield, we still got full oxidation once we got to high enough temperatures and pressures. And here, this change can be explained by the change in the relative permittivity of water. So like I said, at 250 degrees, you have a peak in ionic product, but that a peak implies that it starts to decline. But as you approach the critical point, what happens is that the relative permittivity of water changes. Now, what the relative permittivity is, it's the ratio between the absolute permittivity and the permittivity of free space. And, you know, like, okay, well, what does that mean? Well, in terms of this particular reaction, that relative permittivity is what governs the solubility properties of water. And so under normal conditions, the relative permittivity of water is about 80, which is quite high. And this high value is because under normal conditions, water is quite polar and it has a very preferred structure to it. But under supercritical conditions, the the relative permittivity ranges from about 1 to 10. And that range is really just down to the pressure in the system. And a low dielectric constant means that the water is no longer polar. So in effect, its solubility properties flip. So if you remember from sort of your first year chemistry class, you probably heard something like dissolves like. So a polar substance will dissolve a polar substance. So, you know, you have something like salt dissolving in water. Okay, that all follows. Well, the opposite is true. So non-polar species can dissolve in non-polar fluids. And because that supercritical water becomes non-polar, then the non-polar species that we've created, which is the hydroxide and oxides on the surface of the particle, dissolve into the water, which means that now that any formed hydroxides are no longer coherent. They can no longer passivate the aluminum beneath, which means that fresh aluminum is constantly being exposed to the water. And so that way we can get this full yield or full reaction, even with relatively large particles. And I think that change in relative permittivity is especially interesting here, right? Because we have this can, which has a coating on it, and at 350 degrees, there's no significant hydrogen production. It's very superficial damage to the coating. But once we tip into that supercritical regime, we're left with this extremely fine powder. And this is because of, again, the change in the water. So aluminum cans, drinking cans, are coated to prevent corrosion. And this is just a corrosion reaction. And so it would make sense that they would have a layer on them that will prevent attack from something like a fluid that is rich in OH ions, so something basic, because sometimes these cans have to store basic things, sometimes they have to store slightly acidic things, and so they're coated to prevent that corrosion so that your aluminum can sit on the shelf quite some time. But once you're in that supercritical regime and you have this fluid which can dissolve things that are non-polar, well, now that polymer coating on the inside of the can is no longer doing that anti-corrosion work because it's just being eaten up by the supercritical water, and so you end up with complete oxidation of the aluminum beneath. So I'll just end here. So these metals, when we look at the fact that they're effectively inert or non-reactive under normal conditions, means that they are a safe and stable way of storing and transporting clean energy. And so what I was able to show in these experiments is that under 250 degrees, these metals are effectively inert. Now, once we get above 250 degrees, we get these changes to water properties, which effectively will self-catalyze the reaction. And so here you can get much greater yields than what would have been predicted just by increasing the temperature. And then finally, once we use supercritical water as the oxidizer, well, this ensures that we can get that complete conversion of aluminum and aluminum alloys just by going to higher temperatures. And also by going to these higher temperatures, we get the gains that are associated with having a higher quality heat produced by the reaction. So some of the sponsors who have supported this work over the years are NSERC and FRQNT, as well as some internal funding from McGill and the Vanier Canada Graduate Scholarship Program. And so this is my last slide. So I guess I'll return it to our hosts and open the floor to questions.
Yeah, sure. Thank you, Keena. Very interesting talk. And we got already one question in the chat, and have promoted Huangxin Li to the panelist. I wonder if Huangxin wants to directly ask to Keena, or you prefer us to read the question? Probably I will just read the question, and yeah, it will be easier. The question is a general question. Why do you use aluminum to generate hydrogen as a fuel rather than use it as a fuel directly, like making a aluminum oxygen battery? What is the advantage and the disadvantage?
Well, again, so there's two ways that our lab group is actually using aluminum as a fuel. And so in my branch, it's the aluminum water reactions to produce the heat and hydrogen, but there's a whole other group of students in our lab group who's doing the direct combustion route. So here, just burning it in air to produce the heat directly. And And so there's a few papers out there, and I'm happy to share them if that's something that you're interested in terms of looking at the direct combustion of metals. Now, with aluminum air batteries, that's also a really interesting area of research, but I'm thinking about aluminum as a fuel and energy carrier in terms of more energy trade and seasonal energy storage. And so with both of those applications, the specific energy of your device becomes really important. And the aluminum air batteries, although much higher energy densities than something like a lithium ion battery, because they can rely on air as the oxidizer, there's still a lot of sort of apparatus around that. And so the specific energy and energy density of the batteries are still much lower than just using the fuel directly in either a water oxidation regime or an air oxidation regime.
Thank you for your answer. And we have another question from Dia from McGill. Her question is, in the supercritical state, does all the water react with the metal? Or if not, how do you recover or dry the powder?
Okay, that's a great question. In the apparatus in the lab setup, we actually are going what would be thought of as extremely fuel lean. So the stoichiometric ratio of water in an aluminum water reaction for the slimmest one, the one that requires the least amount of water, is about a 1-to-1 ratio. In my reactor, I'm operating at about 27-to-1. So that's an extremely lean fuel. But having the high amount of water for the research purposes is really important, because that helps us keep a more isothermal environment inside the reactor. The reaction is so exothermic. So if you were to have simply a stoichiometric ratio of that 1-to-1, you would be seeing temperatures, I think, around 1300 Kelvin. And so that's the case that you were describing, where all of the water would be consumed into the, all of the water would be consumed and split into the oxygen, which would oxidize the metal, and the hydrogen, which would be released, and then of course the heat. But in the lab setup, we're less worried about the water issue and the water scarcity issue. So we just effectively flood it so that we can get better, so that we can create those isothermal reactions and sort of like disambiguate between the effects of the increase in temperature from the reaction versus the increase in temperature, just because we're controlling the increase in temperature. So does that answer the question?
Yeah, she says yes.
Okay.
In the chat. Yeah, great. We have a question. We have one of our panelists, Xiaocheng Li, raised her hand. Xiaocheng, would you want to unmute yourself and ask a question directly?
Yes. Thanks a lot for your great talk. It's really cool that I have never thought about the metal water reaction in the bigger picture of the global energy supply. And it's also really cool that no matter what the shape and size of the metal or aluminum, you always see the full conversion at the same temperature, which is the critical temperature. But I guess the shape and size of the metal still has some influence in the reaction, right? Such as probably the rate that you don't talk about. So can you comment on what's the influence of the shape and size on the reaction?
Yeah, absolutely. So the metal water reaction is a surface reaction, which means that the surface to volume ratio of your particle is always going to influence your rate. And so the higher that ratio is, the faster your rates are. And so that's why, one of the ways of increasing reaction rates has just been to use nanopowders, because of that high surface to volume ratio. But with nanopowders, you can get accidental oxidation at lower temperatures. So what we're looking at now is sort of trying to find that balance between something that's cheap and easy to make at sort of, with very easy and very inexpensive manufacturing and so something that's cheap and easy to make, but also something that has that high surface to volume ratio. And so, Others may disagree, but I think the money is going to be on larger micron powder spheres, or something that's relatively sort of roundish, because I think that will be where that trade-off is between, acknowledging the surface to volume ratio, but also having something that's effectively inert under most normal conditions.
Thank you. And I have a follow-up question. So you talk about the recycle of the metal, but I see after the reaction, it becomes like really fine powders. Does that mean you need to like reshape the powders to like a larger size to use them again?
Yeah, again, another great question. So with smelters, they tend to want micron-sized aluminum oxide. And so what we've produced is within the size range of what a smelter would like. They do have concerns about powders that are too fine. So something that's sort of in that like sub-micron size, and that's just because of the physics of dumping something into a cell. If you have something that's too fine, it becomes airborne rather than going into the cell. So they just want things that are big enough, therefore heavy enough to fall when they're loading it into the Hall-Heroult cell.
Mm-hmm.
That's the main concern. And so with that, we're landing at about 30 micron for the products, and that seems to be well within the tolerance range for most industrial smelters.
Okay, cool. Thank you.
You're welcome.
We have another question from the audience. It's from Pascal, and I will try to promote him to the panelist. Yeah, just 1 second. Pascal, if you want, you can ask directly to Keena.
Hi, do you hear me?
Yes.
Yeah.
Yeah. So I was wondering, do you think if there's not enough excess water for the reaction, do you think the water can become saturated with oxide and then prevent the reaction to have 100% yield in the hydrogen?
Yeah, that's a good question. So, we're starting to look at design of these systems. And one of the big question is, okay, do we have the heat sink on the inside of the reactor or on the outside of the reactor, right? So with the lab scale, that heat sink is on the inside of the reactor, so I never have to think about how much water is in the system. Now, of course, if you run out of oxidizer, like in any oxidizing reaction, yes, the reaction will cease if there's not enough oxidizer in it. But to be honest, I've never thought about that question of, what if there's still water, but it can't get to the aluminum? That is a very good question that I think we're probably going to talk a little bit more about.
All right, thank you.
Yeah. You're welcome.
Yeah, hi, Keena. Okay, it comes to my turn. Great. So I have a question. So what is there any downside of going to high temperature?
The high temperature is easy. It's the high pressure that's hard.
Oh.
Yeah. So it's a challenging system to design in terms of to move to something that's commercial. Just because we have, as engineers, we're very, very comfortable with going to high temperatures. We do it all the time. We're very, very comfortable with going to high pressures. We do it all the time. Once you start to combine those two, it just becomes a more challenging system to design. And then, of course, we're throwing in supercritical water, which is incredibly corrosive. Yay for producing hydrogen from aluminum, but like not so great when you think about every other component in the system. That's sort of the. I don't call it a downside, but I do recognize that it's an engineering challenge to deal with that.
Yeah, I see. Yes, and yes. So if we have time, I have another question, more general about. So for fossil fuels, especially gasoline and oil, so it's rich in certain regions like Canada and the Middle East, but it's very rare in other places like Japan and some European countries. So we are going to use aluminum. So like, is it like equal accessible to different countries, or same as oil?
Yeah, again, and I think that's a really great question, right? Because there is this parallel. So we think of like, oh, well, we can get gasoline anywhere, so it's always available. But you're right, like it is unevenly distributed around the world, you know, and then also renewable energy is also unevenly distributed around the world. And bauxite, which is the ore from which aluminum comes, is also unevenly distributed around the world, right? So we're used to dealing with systems that are unevenly distributed around the world. We already do it with a hydrocarbon system. And so now we're just switching it to another system. You know, the bauxite tends to be very rich. There's a lot in parts of South America, Australia, parts of West Africa. Jamaica also has quite a bit. So, you know, geographically, like that's actually kind of a nice distribution because you can get like to your North America, Western Europe, Africa, Asia, and Australia. Like we have like a nice distribution. And then it comes, okay, well, we also need to marry that with the cheap electricity, right? That's how the aluminum industry functions today, is that it takes the bauxite wherever it's available because they don't have any control about that, and then they move it to where there's cheap electricity. And then you end up with a situation like in Quebec, where we have extremely cheap electricity. We're also the 4th largest producer of aluminum in the world. We don't have any bauxite reserves anywhere near us. Yeah, so that system and thinking of like moving things around is, I think we're already quite comfortable with that. And so I don't think that will be a big impediment.
Yes, thank you. Yeah.
You're welcome.
Yeah, Keena, I have a follow-up question just regarding this high temperature, high pressure environment. I think you have done this analysis, but I don't recall like what's the result is. Like what is about the energy accounting, like the energy produced by the hydrogen yield comparing to the energy that you need to create this high pressure, high temperature environment, right?
Yeah, so the short answer is that relationship is negligible. Okay. So yes, when people like in the lab, you know, I have a reactor with a heating band on it, and that draws a certain amount of power to heat everything up. Yes, of course, right? But once you have that once the reaction starts, so if you can imagine this is how it would actually be rolled out, this is what it would look like in an application, is you would have some sort of flow reactor. So it would be going, and it's so highly exothermic that the challenge isn't keeping it under supercritical temperatures and pressures. The challenge is actually removing enough heat at a fast enough rate to maintain the temperature at where you. Okay, yeah, I mean, if you think about striking a match or burning, like any other combustion, right? Like it's you have an ignition, and then it just goes until it runs out of fuel or oxidizer.
Oh,
and it's the same here.
Okay, so I can understand this this energy input to create this high temperature, high pressure is kind of like the ignition energy, like the spark in the internal combustion engine. Okay, I understand. Okay, great. Thank you. Thank you. I have another one of our panelists, Xiaocheng, raised his hand. Xiao, please, if you can ask your question directly.
Hi, thank you. Thank you very much for the great talk. Yeah, I just have one question because I think aluminum, it doesn't just exist in the nature. You have to mine them. You have to, deal with it. So I'm wondering, how does the cost compare to say you're mining the oil, converting it into fuel? How is the cost compare in terms of financially and also environmentally?
Yeah, great. That's a great question, and that's part of our ongoing work now, is to do that kind of analysis. You know, I have a paper. It's an applied energy that answers this question, and so we did sort of just a very initial first pass Okay, like if we wanted to compete with diesel, right? Because diesel is really the fuel of remote places that don't have renewable electricity, right? So that's really what we want to displace. Okay, so diesel, you get it from oil. Let's say, and I benchmarked it at $50 a barrel or $100 a barrel. And that's sort of your high and low in terms of oil prices that can keep an economy going. And so that translates to diesel that comes out at about 4 cents a kilowatt hour to 8 cents a kilowatt hour, right? So if we want to displace that, that's how aluminum has to be cheap enough to displace that. And off the top of my head, I think that aluminum, if it came in around, I think $900 or so a ton, it could displace that. If you compare that to the market price now, aluminum is around $2,000 a ton. So quite a fall would be needed. But what we also think about when we, sorry, I didn't mean to go forwards. I meant to go backwards in my presentation. So when we talk about the aluminum fuel cycle, one of the things that we always highlight is this bit here, right? It's bringing the oxides back. So when you think about something like burning a hydrocarbon, the oxide escapes to the atmosphere, and that's why we're in trouble now. Whereas here we have these solid oxides that can be brought back for recycling, but these solid oxides have a value. So if you just go and you look at the value of aluminum oxide on the market today, it's sitting around $300 a ton. And for every ton of aluminum you oxidize, you'll get about 1.8 tons of alumina. So while again, we're working out the economics, because this kind of closed loop smelting it's not done in the industry now. And so we're still trying to figure out what the economics of that would look like. But we're hopeful that it will eventually be cheap enough to reasonably compete with something like diesel that has a reasonable carbon tax attached to it.
Okay. All right. Yeah, thank you for the answer. And yeah, just what about environmentally? I'm assuming, yeah, I'm assuming producing aluminum for mining, I think it could produce quite a lot of pollution.
Yeah, so great. So with the life cycle of bauxite, or the life cycle of aluminum, actually, I'm gonna just skip forward because I had a couple of slides on this and then I took them out because I was worried about time. But this is sort of like what the aluminum fuel life cycle looks like, right? So the first step is the bauxite mining. And so these are all just normalized to 1 kilogram. So there's some amount of energy that's just for the mining. And then there's some amount of energy for what's called the Bayer process. And this Bayer process is how you go from bauxite to aluminum oxide. And then there's some amount of energy to reduce the aluminum oxide into aluminum. And you end up with that 31 megajoules. Now, these two processes, the carbon emissions come from high temperature processes and from vehicle fueling. Right. So again, if we're dreaming about a whole energy system that's transitioned, then the carbon emissions here would be minimized because we would have electric or hydrogen fueled vehicles. And so, okay, we could get rid of that. And because there's no process emissions, and there are pollutants that are non-carbon pollutants that are involved with the Bayer process. But it is a somewhat closed loop. But the other thing is that, sorry, this part for each kilogram, we only have to do that part once. We just have to, and then once we have that aluminum in the system, we're just going back and forth between these two. Now, when we get to the Hall-Heroult part of the process, and so this is the aluminum production, that's where currently we see process emissions because of the use of carbon anodes in the Hall-Heroult cells. But the reason that I'm still very optimistic about this is that as we speak, there are inert anodes that are being rolled out that would replace those carbon anodes. And these inert anodes, they can be used in existing reaction cells. So it's not as if you would have to shut down all of these smelters and rebuild new smelters. They can be swapped out and retrofit in. And once that's done, then this step here, there are no carbon emissions or no process emissions involved in it. Yeah.
That's very cool. Thank you.
You're welcome.
Thank you. Yeah, is there any other questions? It's probably our last call. So, yeah, if there is not, then I would like to thank our speaker, Keena Trowell, again for her very interesting, very informative talk and for her time preparing the talk. And I would like to thank you all for attending today's event and for all of you asking questions. Yeah, Jen, would you want to give an announcement of the next talk, or we can conclude at this point?
Yeah. Hello. Yeah. Thanks so much for Keena's talk. It's really informative, and I actually asked some questions to Xiaocheng in the background because I think it's kind of repetitive to the other people's question. And so the next talk will be from Vivian from Harvard, and probably on bioelectronics, on the topic for bioelectronics. So hope to see you guys in the next talk. Yeah. Thanks.
Yeah, thank you all. Thank you all, and also thank Weiqi for co-hosting, and thank Keena again for your time. Yeah, have a good day. Yeah, thank you.
Yeah, thank you. Bye bye.